Okay, so I am now going to show you two different ways to write the Collatz program. So in other words, what I mean when I say write the Collatz program, the input is going to be a number, and the output is going to be the number of terms in the Collatz sequence for that number. So like if the input is 4, in the Collatz sequence there are 3 elements, 4, 2, and 1. If the input is 3, the output should be 8, because in the Collatz sequence for 3 there are 8 terms. Okay, so I'm going to call this I'm going to call a function Collatz. I'm just going to call it COL, so we don't have to keep on writing Collatz. I'm just going to take a number in. Now, one thing that I do want to mention, this has been mentioned in the discussion comments. If you're familiar with with functions in other programming languages, a lot of times in this area right here, well, a lot of times you might not even write the def, but a lot of times in this area right here, before the name of the function, you put its return type. In other words, like the thing that it is returning. So this function up here returns a number, so we would write, double up here, meaning it's returning a double precision number. If it's returning an integer, you might write int, that sort of thing. And also, many programming languages will require you to tell the function or the program what type of input this is. So maybe if I'm expecting an int, I would have to write int there. Now, Python, as we've discussed, or as you've seen people discuss in the discussion forums, is not strongly typed, and so you don't have to do that. But you can do things called type hints. I'm not going to talk about that. It's been discussed in the discussions. You can ask about that more in the discussions, or look it up on your own. But it's just kind of sort of a middle ground between strongly typed and Python. And the people who are experts can tell you more about why that's something that you would want. But I think it seems like an obvious thing to want, kind of gives you a good middle ground between the two different extremes. At any rate, here's what we're going to do. So this needs to return the number of terms in the Collatz sequence. So basically, we're just going to compute the Collatz sequence for n and count the number of steps. Okay, so what we're going to do here then, remember, so just like in this program, just like in the program we did before, we had a loop where we had n, we either multiplied it by 3 and add 1, or divided it by 2, and we changed that value of n. We're going to do the same exact thing here. So I'm just going to, before I even think about counting the number of items in the loop, or the number of items in the sequence, I'm just going to write a while loop that does that computation. So while n is greater than 1. Okay, so if n is even, if this is even, n is equal to n, and I'm going to use the integer divide, or the divide and take the floor item, else n is equal to 3 times n plus 1. I do want to point out one thing. So this idea of, actually I'll point that out in just a little bit. Okay, and then now what's going to happen, it doesn't matter what number we put. If I do Collatz of 3, all that's going to happen is going to come up and just do this. It's not going to return anything. It's not going to do anything except for within the program, it's just going to do all of these computations. So not very exciting. Okay, so now what I need to do is I need to introduce a counter. I'm going to call it counter. I'm going to start it at 0. And at every step in this computation, I need to add 1 to the counter. And then that is the thing that we're going to want to return. Now, Now, what's going to happen? You might already be thinking about this. Now, what's going to happen is we're going to have a very common type of error called an off by 1 error. I know that when I run this program on the input 3, I should get out 8. But I'm going to get out, well, I want you to think about what we're going to get out, and then think about what the problem is going to be. So I'm going to run this, and we're going to get 7. Okay, so think about a little bit what's happening with the problem. Maybe pause it and think about it. Okay, so what's happening is when I run this program, let's think about what's happening. So I run it with the input 3. Counter, okay, so once I enter into this program, n is equal to 3, counter is equal to 0. While n is greater than 1, we're going to do something. Okay, so counter is greater than, or counter equals counter plus 1. Okay, so if n is even, we're going to do something. Nope. If n is odd, so it's not even, so we're going to do something else. We're going to multiply it by 3 and add 1. Okay, so now n is equal to 10. So we're going to go through this again. Counter equals counter plus 1. Yes, n is even, so we're going to divide this by 2. So now n is equal to 5. We're going to go up here again. We're going to increment the counter. N is odd. We're going to multiply it and by 3 and add 1. That gives us 16. Okay, and then we go through this again. N will be equal to 8. We do this again. N will be equal to 4. We do this again. N will be equal to 2. We do this again. N will be equal to 1. Now, if n is equal to 1, we're not going to increment the counter. So this does not increment the counter when n is equal to 1. So we need to make that adjustment. For n is equal to 1, this does not increment the counter. So there's a couple of ways we could do this. We could either return counter plus 1 down here, or I could just make this counter equals 1 up here and return counter down there. I'm going to keep this as 0 and return counter plus 1. And the reason is because this does count this when n is equal to 3. See, if I set like this counter to equal to 1, it's kind of like saying psychologically we would be counting for n is equal, computing the, let me get my thoughts here a little bit. If I do this, if I do counter is equal to 1 and then do like this, psychologically, I think about this as starting the counter as 1. In other words, we're like counting it, we're counting 3 when we say counter is equal to 1, we're counting the first term of the sequence, which is 3. And then when we start here, we're counting 3 again. But everything works out in the end because we don't count it for when n is equal to 1. I realized that was kind of clunky. If I counted at 0 here, when I do this while loop, n is equal to 3, and so I'm putting 3 in my sequence. Psychologically, I'm putting 3 in my sequence for the Collatz function, and I'm incrementing the counter. Now what happens when n is equal to 1, we don't do this. When n is equal to 1, remember, the Collatz sequence for 3 is 3, 10, 5, 16, 8, 4, 2, 1. The way the program is now, when n is equal to 1, we don't do this. It's like when n is equal to 1, we're not putting it into the sequence because we're not incrementing the counter when n is equal to 1. Okay, but this program always ends, at least, up to numbers 10 quadrillion or whatever. It always ends in 1. So I'm just going to return counter plus 1 like this. Okay, this in my mind is incrementing it, is incrementing the counter for the n equals 1 case. Or we could even do something like this. Counter equals counter plus 1 if you want to increment it, kind of explicitly for n is equal to 1. There's all sorts of other things that get a little maybe silly. If n is equal to 1, we're going to increment the counter. Okay. Those are all valid options. I'm going to do return counter plus 1. Okay, the other thing that I want to mention here is this operation of incrementing something or dividing something by 2 and then replacing it in. This is very common. And so there's an idiom that we can use here. Instead of doing counter equals 1, we can do counter plus equals 1, and that has the same effect as doing counter equals counter plus 1. And similarly down here, we can do this. We'd have to make this little compound if we want to. We could do n times equals 3, and then n plus equals 1, something like that. Okay, maybe there's other ways to do that, but this should now give us the correct output. Okay, let's test it on something else. Well, if I put in 16, what's in the Collatz sequence for 16? Well, 16, 8, 4, 2, 1. I should get 5 when I run this. Good. If I do. So it's always good to test the edge cases. If I run 1, I should get 1. Okay, so now here's something interesting. What do you think is going to happen if I put 0 in? Okay, try to run through the code to see what's going to happen if you put 0. So if you run it, well, oh, sorry. I guess n is not, so it's not going to do any line in this code because it starts because it says n is greater than 1. If you had something like here, while n does not equal to 1, this program would run forever. Okay, so that was a little less exciting than I thought it would be. Okay, so now I want to show you a recursive version of this program, and one of the two main things that I want to show you are a recursive program, and sort of the secondary thing is that I want to show you how we can write a function that has what are called default arguments. So I'm going to call this function the Collatz function, but it's going to be a recursive function. Recursive functions mean that the function will call itself. In the body of the function, it's going to call itself. It's going to refer to itself. But this really is how the collat sequence is defined. If I want to know what the collat, if I have a number, if I start with a number, let's say 3, and I want to know what the 5th term in the collat sequence is, I have to know what the 4th term in the collat sequence is, right? Because the next term, the n plus 1th term is defined in terms of the nth term. Okay, so again, what I want this to do eventually is just to output the number of terms in the collat sequence for n. I'm going to forget about the counter for just a minute. So if n is equal to 1, we're just going to return. We're going to return n, which would be 1. I'm just going to get the basic body of the program and the logic of the program worked out now. Else, if n, so I'm going to use this. So if n is equal to 1, we're going to do something. I'm going to use this elif. It means else if n is even, we're going to do one thing. So if n is even, we're going to do something. I'm going to write that, and then we're going to do something if n is odd. So if n is even, what we're going to do is we're going to call this function the recursive function, but now the input is going to be the integer version of n divided by 2. Okay, and we're going to say return this number here. If n is even, what we're doing is we're calling this program again on the input n divided by 2. And then finally, it's going to be odd. We're going to say return return the recursive version of collats 3 times n plus 1. Okay. And again, this is not going to give us a counter. This is just going to kind of, we're going to make the program compute the collat sequence for a number, but not actually return anything. Okay, so let's think about what's going to happen if I put this. I'm going to run this line here. Let's think about what's going to happen if I do this on the input 3. So collats col recursive 3 is going to come up here. If n is equal to 1, okay, n is not equal to 1. If n is even, n is not even, so it's not going to do that. Okay, so else is going to return collats of 3 times n plus 1. Okay, so now it's going to do the computation collats of 10. Okay, so now it's going to come up here. N is equal to 1. Nope. Is n even? Yes. So now it's going to return collats recursive 5. Okay, and so now once we do collats recurse 5, n is not 1, n is not even, so it's going to return collats recurse of 10. Okay, then it's going to return, it's going to come up here, collats is even, oh sorry, not 10, 16, collats is even, so collats is going to return n divided by 2, so it's going to return 8, or it's going to call collats of 8, then it's going to call recursive 4, collats recursive 2, and then finally it's going to call collats recursive 1, so n is equal to 1, it's going to return 1. Okay, so if I call collats recurse 3, it's just going to return 1. So it's going to return 1. It doesn't matter what it's going to return. Okay, but remember, we don't want to return the last element of the sequence. We want to return the number of elements in the sequence. So then what we're going to do is we're also going to have an argument passed called counter. And each time this function is called, it's going to increment the counter by 1. So counter plus equals 1. Okay, so now if I do this here, if I try to run this program, I'm going to get an error because it says, wait, this function takes in 2 arguments. You only gave it 1. So now what we need to do is we need to start off the counter at 0. So I'm going to do collats recurse 0, run this. Whoops. Oh, sorry, I also have to, so now we're going to return the program here. I need to add the counter argument here. You might have been yelling at your computer just a minute ago. And so now we're going to not return end, but we're going to return counter. Now, almost certainly there's going to be an off by 1 error here. So what's going on is I'm starting the counter at 0 because before I compute a collat sequence, there's nothing in it. I haven't even added the 3 yet, psychologically. So this is what I'm going to have. If I run it, I get 7. Okay, so here's the problem. Here's a problem. Again, I'm not including, just like up here, when n is equal to 1, I'm not incrementing the counter. So I need to increment the counter here. And I'm going to run this, and now if I run it, I get 8. Let's see what happens if I run it on the input of 16. Yes, I get 5. Is that right? 16, 8, 4, 2, 1. Okay, if I run it on 32, I should get 1 more than that. Yep. Okay, so this, again, I've tested it. Oh, let me test the edge case of 1. I get 1. Now, if n is equal to 0, I think we're going to get a program that doesn't terminate. Okay. So this is a recursive program. Yes, thinking through recursively is a little bit difficult. But you just, again, it's a way to compartmentalize what's happening in the program. Okay. Now, one downfall about this program is that oftentimes, if I just want to know the number of terms in the collat sequence, the program should not force me to put a 0 there. I should just be able to write this, because that's what I want to know. The thing that I want to know now is the number of terms in the collat sequence for 3. Making me put the 0 there is kind of like forcing me to like partake in what should be the inner logic of this program, which I, as a person calling the function, really should not be doing. So what Python lets you do is provide default arguments. So I'm going to say counter equals 0. So what this means is if I have one argument here, it's going to say that the first argument n is equal to 3. If I don't have a second argument, it's going to it's just going to set counter equal to 0. But note down here, I'm putting in one argument. I'm putting in 2 arguments here. So if you put in an argument, if you tell the argument, if you tell the function what the argument should be, it's going to use that argument. If you don't tell the function what that argument should be, it's going to use the default argument, which in this case is 0. So I can run this, and I'm going to run this, and I'm going to get 8. Now, if I do something silly, which there might actually be a reason that you want to do this, if I put in 2, now when I run this, I should get 10 because I'm starting the counter at 2 instead of 0. Okay, at any rate, this is kind of all that I wanted to talk about. This gives a brief overview of recursive functions and also default arguments, which is what's happening here. Okay, that's it for this video.